Hi students, welcome back to Wisdom Academy YouTube channel. In the previous video, you have learnt about parallel plate capacitor. In today's class, we will see some numericals, then we will move to the next topic. The first numerical is calculate the total charge that flows in the circuit when 100 volt battery is connected between point A and point B. So in the previous video itself, I have told about the capacitor in series and capacitor in parallel. Please go to that video if you have not seen it yet. Right. So what you have to find? You have to find the total charge that flows in the circuit when 100 volt battery is connected between point A and point B. So before going to that step, you must find the equivalent capacitance between A and B. And to find that, we have to simplify the circuit first. You can see very clearly that 60, 60 and 60, these three capacitors are in series. Someone may ask that how to find whether a capacitor is in series or parallel. For that, what I suggest is pass a charge from here. If the charge gets splitted up, it is parallel connection. If the charge goes same in all the capacitors, it is series connection. So the charge comes here, see these two branches become splitted. So these two definitely will be in parallel. But see this what goes here, same goes here and same goes here. So same path is followed. So these three are in series. So these three capacitors, when you find the equivalent capacitance, since it is in series, it will be 1 by Cs is equal to 1 by 60 plus 1 by 60 plus 1 by 60. And that will be equal to 3 by 60. So Cs will be equal to 20 microfarad. So 20 microfarad is the equivalent capacitance between this point and this point. Now let us draw a simplified diagram once again, and I will get like this. Here 40 is there, and here already 10 is there, and another 10 is there, and another now we have found that 10 is there. Like this we have made. This is 20 microfarad. These two are given as 10 and 10. And this is 40 microfarad. This is a simplified circuit between A and B. So whenever the complex circuit is given like this, you have to first simplify that. It will be easier for to solve. As you experience or as you practice more, then this simplifications you can do without even solving it itself. That command will come when you practice more numericals. Now this 20, 10 and 10, all three are in parallel connection. So when all these three are in parallel connection, their equivalent capacitance will be the addition of this. So C parallel is equal to 10 plus 20, that gives me 40 microfarad. So here I get the value as 40 microfarad. This is the capacitance between here and here. So I'll get a simplified circuit as like this. Now between point A and B, already 40 microfarad was there, and equivalent capacitance of these three came out also as 40 microfarad. Very easily we can say that between A and B, these two capacitors are in series. So what will be their capacitance? 1 by Cs is equal to 1 by 40 plus 1 by 40, and when I take the LCM, 2 by 40. So Cs becomes equal to 20 once again. So Cs is 20 microfarad. This is the capacitance of the capacitance between point A and B final. So I got the equivalent capacitance as 20 microfarad. This is between A and B. What they have asked in the question, they have asked to find the total charge if 100 volt battery is connected. So V is given as 100 volt, and they have asked you to find what is Q. So we know that Q is equal to C into V. So what is C? C is 20, V is 100. So I will get 2000 coulombs. I should say microcoulombs because it is microfarad. So if you have a capacitance 20 microfarad and potential difference of 100 volt, I will get the charge as 2000 microcoulomb. This is the answer for this question. Next question. This kind of questions are frequently asked in examinations where they will give you infinite capacitance. This is also true in resistance case. Infinite capacitance or infinite resistance questions, how to solve it, I will tell you one example today. So in this what they have given, there are infinite number of rows, and in each row the capacitance goes like this. In this 1 capacitance, in this 2, in this 4, this will be 8, and it goes so on. In this row it has 1 capacitance, here we have 2 capacitance, here we have 4 capacitance, and here we have 8, and it goes so on. So what they are asking, what is the equivalent capacitance between A and B if there are infinite resistances, infinite capacitance arranged like this in the different rows. We know that the net capacitance in the case of parallel connection will be C1 plus C2 plus C3. So one thing is very sure, CAB will be equal to C1 plus C2 plus up to C infinity. Am I right? Now let us try to find what is the value of equivalent capacitance in each thing, in each row I will say. So in the first row, I know it is 1 microfarad. In second row, they two are in series, so it will be, we can have to find like this, 1 by C2 is equal to 1 by 1 plus 1 by 1, that is equal to 1 by C2 is equal to 2. So C2 will be equal to 1 by 2 microfarad. So let us say, in the same way, let us try to find what is C3. C3 will be equal to 1 by, 1 by C3 is equal to 1 by 1 plus 1 by 1 plus 1 by 1 plus 1 by 1, that is equal to 4. So C3 is equal to 1 by 4 microfarad. Am I right? In the same way it goes. So 1 by C4 would be probably, these numbers like this, 8 will go and 8 will come. So C4 will be equal to 1 by 8 microfarad. So now I get the value of CAB as equal to 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus dot 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 till infinite. So now this became an infinite geometric progression. Now from here this question turned into a mathematical question. So this is an example of infinite geometrical progression. So how to solve this? Summation of infinite geometric progression is equal to CAB will be equal to A by 1 minus R. I hope you remember this. A is the first term, R is the common ratio. So first term is 1. So 1 by 1 minus common ratio is 1 by 2. 1 by 2, 1 by 2, 1 by 2 is going. So 1 by 2. Now let us solve this. 1 minus 1 by 2 is 1 by 2. So 1 by 1 by 2 and that is equal to 2 microfarad. So if you arrange 1 microfarad capacitors in this fashion where you have one capacitor, 2, 4, 8 and so on till infinite, the net equivalent capacitance will be 2 microfarad only. Let us see one more question of infinite resistance. In this question again you have to find the equivalent capacitance between A and B in such a way that 2 microfarad, 1 microfarad, 2 microfarad, 1 microfarad are added like this infinitely. There are infinite number of things like that. So how do this kind of question? What I will do, I will assume this whole thing to be C. Let me assume that all these capacitances together gives me value of C. And then in this C, I will add this 2 and 1. So this 2 and 1 addition will not affect the answer much because it is already infinite. If you add anything in infinite, it does not matter much. So it happens like this. This is point A and point B. So this complete infinite I have taken as C and this 2 and 1 I have attached to it. Now let us try to find what is the equivalent capacitance. So first these two are in series. So C net will be equal to, for these two branches, C net will be equal to 1 by C net will be equal to 1 by 2 plus 1 by C, that is equal to C plus 2 by 2C. This is 1 by C net. So C net will be equal to 2C by C plus 2. This is for these two things, and then this and this are in parallel, so it will be added up. So C will be equal to 1 plus 2C by C plus 2. Some people may say me, why you are going to C again here? Because C is the net capacitance of the infinite circuit. That's what it will be this. Now when you solve this, it will become C is equal to C plus 2 plus 2C by C plus 2. It goes this side, becomes C square plus 2C is equal to 2 plus C plus 2C. This 2C gets cancelled. It comes this side. I will get C square minus C minus 2 is equal to 0. Quadratic equation. Solve. You will get C is equal to minus B. So minus 1 plus or minus root over B square minus 4AC. So 1 minus 4 into A into C, 8 plus 8 will come by 2A, that is 2. So you will get C is equal to 1 plus or minus root 9 by 2, that is equal to 1 plus or minus 3 by 2. So the answer will be either 4 by 2 is 2 microfarad or it is minus 1 microfarad. See, the capacitance cannot be negative. So the answer is 2 microfarad. So net capacitance between these two things is 2 microfarad. Next topic is energy stored in a capacitor. So already I have told you capacitor is a device used for storing the energy. Now how much energy is stored we are going to see now. When I talked about the principle of capacitor, I told you that we will have one charged plate and one neutral plate. On this plate we will supply charges it will make this plate fully charged, and by the principle of induction there will be some charge coming on this, induced on this, and then same charge we will take out by using earth. For that you can see that video where I have talked about the principle of capacitor. So what I will do, I will supply some charge to it, make it fully charged, and then by the principle of induction this will acquire negative charge because the positive charge will be sent back through earth. Now there are two ways we can derive the equation of energy for a capacitor. One way is by not using integration and one way is by using integration. I will tell both the ways to you, but for exam always use integration method because many teachers will not accept that non-integration method of finding the energy stored in a capacitor. So that is a bit easy way. So I will tell the easy way first. So please try to understand that we know potential is equal to work done per unit charge, right? I hope you have understood by now that potential is work done per unit charge by now. So let us start charging this plate. So when one charge was sent, it was easily sent. When second charge was sent, it was a little difficult. Why it was difficult? Because this charge will repel that charge. So we must do some work in order to put the charge inside this plate. Same way when you are putting third, fourth, fifth and sixth, as you keep on putting the charge on this plate, it becomes difficult for you to put the charge. The reason is there is a repulsive force from that charge. And what work you do in pushing all the charge on this plate is stored as energy in the capacitor. So what you come to know, initially when there was no charge on this plate and you send the first charge, the initial work done was 0. Why it was 0? Because there was no much force required to send it inside, just like that it went. But as you keep on going, your work done kept on increasing and the final work done was V into Q. So as you can say that as you sent, the potential kept on increasing and a time came when the potential became maximum. So initially the potential was 0 and then potential became maximum. Now what is the net work done, or I should say that average work done, that is equal to Vi plus Vf by 2, and this average work done is stored as the energy of the capacitor, that is U, that is equal to, what is this, 0 plus Vq by 2. So energy stored in the capacitor is equal to half QV. Now as I said you, this is a non-integration method not accepted by many teachers. So I will go to the integration method of finding the energy stored in a capacitor. So for that I will say in this way that a small amount of work done to transfer this charge was dW is equal to V into dQ, right? That small work done to send one charge dQ inside the plate is V dQ. Now what is the net work done? For finding net total work done, we want to integrate it. So integration of dW is equal to integration of V into dQ. Now we know that Q is equal to C into V. So from here you can say that V is equal to Q by C. So I can write this 0 to W. So W is equal to, instead of V I am writing Q by C dQ integration from where to where? From 0 to Q. Am I right? So then work done will be equal to 1 by C comes outside, integration of Q dQ from 0 to Q will be equal to Q square by 2. So 1 by C into Q square by 2. So what I got, this energy stored as a capacitor U is equal to half Q square by C. Someone can say these both are not same. Is it not same? See here, instead of V, if I put Q by C here, then what you will get? You will get half Q square by C. Is it not same? These are different ways how I write the energy stored in a capacitor. I can write half into QV or half into Q square C, or I can even write in terms of only C and you will get a third expression. So what we came to know? We came to know that energy stored in a capacitor is half into QV or half into Q square by C, and you can do by both the methods to find the energy stored in a capacitor. Let us see loss of energy in redistribution of charges. Before I talk about loss of energy, I want to tell you about redistribution of charges. So what is this redistribution of charges? For that I will take two capacitors. Let these two capacitors be at potential V1 and V2, and let the charge on this be Q1 and Q2. So let the charge on these two capacitors be Q1 and Q2. So if these two capacitors are at different potentials, one is at lower potential, one is at higher potential, then we will see there will be a flow of charge from higher potential to lower potential. If I assume that V1 is higher potential, V2 is lower potential, then there will be some charge movement from Q1 and Q1 to Q2, and they both will equalize. This charge will keep on flowing until both become same potential. So remember that initially if it is Q1 and Q2, after this redistribution, it may become Q1 dash and this may become Q2 dash. So in case if I am assuming V1 is more and V2 is less, then Q2 dash will become more and Q1 dash will become less. So now, there is a term called as common potential. Common potential. So common potential will be equal to total charge by total capacitance, because we know that potential is equal to charge by capacitance. Now this common potential V, see, total charge will remain conserved. What charge was there before and what charge is there after, totally it will remain conserved, though it may change for Q1 and Q2. But initially suppose it had 50 and it has 20, then this may become 40 and this will become 30. 10 has gone from here to this, but total charge always remains 70 only. I think you can understand this. So what is total charge? Total charge is Q1 plus Q2 and total potential is C1 plus C2. So the formula of common potential is V is equal to Q1 plus Q2 by C1 plus C2. I can further simplify it because Q1 is equal to C1 V1. So I can write C1 V1 plus C2 V2 by C1 plus C2. It is another way to write the formula of common potential. After redistribution, if the charge Q1 dash, that will be equal to, we know that Q is equal to C into V, so it will become C1 into V, right, and Q2 dash will become C2 into V. Why I am not writing V1 and V2? Because V became common potential now. So if I multiply common potential with capacitance, I will get the charge on redistributed charge on first capacitor. Now from here I can write Q1 dash by Q2 dash is equal to C1 by C2. Now why I have derived this? This gives you an idea that if the two capacitors have different charges and they have different potential, then after the redistribution of charges happens based upon the ratio of their capacitance. So based upon the ratio of their capacitance, the charge gets distributed. Now I will talk about loss of energy. So what happens? It was found that the energy of the capacitor before this redistribution and after this redistribution is not same. There is some loss of energy. That may be because of some heat produced or something, but there was some loss of energy which was found when this redistribution of charge was happening. Let us try to find what is the magnitude of that, how much charge is getting lost. So for that we will find first initial energy. So what is the initial energy? Initial energy of the capacitor will be half C1 V1 square plus half C2 V2 square. I hope you remember the diagram. The diagram is something like this, where I have here C1, here C2, they were at different voltage V1, V2, and initially it was having Q1 and Q2 charge, which became Q1 dash and Q2 dash. So now initial energy was half C1 V1 square plus half C2 V2 square, and what was the final energy? That was half C1 V square plus half C2 V square, because after the redistribution of charge it had a common potential. That's why I have written VV here. So from here I can write it is half C1, if I take V square common, C1 plus C2 into V square. Now what is V? I just derived before some time. V is equal to C1 V1 plus C2 V2 by C1 plus C2. So I will write this like this. This will be equal to half C1 plus C2, and instead of V square I am writing C1 V1 plus C2 V2 by C1 plus C2 the whole square. So this term and one term will get cancelled here, which is, if I write it separately, this square and this square, then one term will get cancelled from there. So I get U of final is equal to half C1 plus C2, and above I have C1 V1 plus C2 V2 the whole square. So what I will do now, I will open up this. So I will get UF is equal to C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2 divided by 2 into C1 plus C2. This is the final energy, this is the initial energy. I will find the loss in energy. So, loss of energy, that is delta U, that will be equal to U initial minus U final. What is U initial? Half C1 V1 square plus half C2 V2 square. I will subtract this term from there. This term will come here. Then what I will do? I will take something common. I will try to take delta U I am finding. I will take half C1 plus C2 as common. That will get multiplied in these two terms. The first term, this term will become C1 V1 square into C1 plus C2 and plus C2 V2 square into C1 plus C2, and then I have this full term, that is plus C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2. I hope you are understanding what I am doing. So, what happens after this? This is 1 by 2 C1 plus C2. If I open up this bracket, it will become, first I will multiply this C1 square V1 square plus C1 C2 V1 square, and if I open this, it will become C2 C1 V2 square plus C2 square V2 square. Already, oh sorry, minus sign is here, so everything will become minus. Minus sign is here, right? So, this will become minus, this will become minus, and this will become minus. So, I will have minus C1 square V1 square minus C2 square V2 square minus 2 C1 C2 V1 V2. Then you will see this term gets cancelled, and this term gets cancelled. So, if I take C1 C2 common outside, what will be remaining here? Let us check that. So, C1 C2 comes outside, it will be remain as V1 square plus V2 square minus 2 V1 V2. This becomes V1 minus V2 the whole square. So, I get finally that loss of energy is equal to C1 C2 by 2 C1 plus C2 into V1 minus V2 the whole square. Now, this is the equation for loss of energy of a energy stored in a capacitor when there is a redistribution of charges. So, one thing you can understand from this equation, that since V1 minus V2 the whole square, whether the charges are distributed or the potential is V1 is, it is moving from V1 to V2 or V2 to V1, it will always be positive value. It will always be a positive value, because this, even if it is negative, square will become positive. So, remember that whenever there is a redistribution of charges, there will be some loss of energy, right. So, in today's session, what we learned, we have seen some numericals in the beginning based upon the series and parallel connection of capacitors, and then we learned about energy stored in a capacitor, and then we learned what is redistribution of charges and how to find the loss of energy during the redistribution of charges. In the next class, I will talk about dielectrics and polarization. Till then, keep on working, solve all the numericals of the textbook, like the video, share with your friends and subscribe our channel. Thank you very much.